Bismillahirrahmanirrahim. In this video, we will discuss about the half-controlled bridge rectifier circuit. In the last two videos, we have seen the detailed operation of the half-control as well as of the fully controlled bridge rectifier circuit. In half-controlled rectifier, the high side switches are the thyristors and the low side switches are the diodes. When you apply a gate pulse to a thyristor, it is turned on provided its anode voltage is higher than the cathode voltage. So whenever a particular thyristor will be turned on, that will turn on one of the diode from the lower side depending upon the voltage. If VAB is maximum in your circuit and you are going to fire the thyristor of phase A, that is D1 over here, so in order to complete the path towards the phase B, the diode D1 will be in the on state. So thyristor 1 and the D1 and diode D1 will be in the on state when this voltage is going to be maximum. And then over here, if your thyristor 1 is on and the reverse path is toward the phase C, then for that your diode D2 will be in the on state. So depending upon the voltage level, the particular thyristor and the diode will be turned on. For detail of this one, you can see the last two videos. Okay, now let's look at the phasors of the line voltage waveforms which are going to appear across your load. So when you are going to turn on the thyristor T1 and along with that, let's suppose D2 is in the on state. So the phase A is connected over here and the phase C is connected with this part, right? So the voltage between phase A and phase C, that is VAC, will be appearing across your load resistance if you neglect the voltage drop across the thyristor and the diode. So this voltage will appear across your load, and load DC voltage at that instant of time can be calculated. Okay, so now if you look at the phasors, let's consider that our this waveform is the reference one VAB and we represent it in the form of phasor. So VAB phasor is shown over here and its angle is 0 degree. This is our reference point, right? And then the second phase is going to start or the second line voltage VBC is going to start at the angle of 120 degree from here, so that you can see over here at the angle of 120 degree in clockwise direction, it will be minus 120 degree with respect to this one. So it is lagging behind, VBC is lagging behind by the angle of 120 degree. And now if I look at the third waveform, that is VCA, so third waveform is this one, and this is further delayed by 120 degree over here, right? So the total angle from this point till over here, this will be equal to minus 240 degree. So your line voltage waveforms are at the angle of 120 degree with respect to each other, right? And out of phase component of that line voltage waveform will be at 180 degree with respect to that particular line voltage waveform. So now if you consider this one VAB, this is with angle 0. So if you look at that one, this is this waveform, right? And 180 degree out of phase of this one is this one VBA. So that will be represented like that. That will be at the angle of 180 degree. So either you come 180 degree in this direction or in this direction, you will get the out of phase component. So VBA is equal to VAB but with the angle of 180 degree, right? Plus minus 180 degree. Either you come in the clockwise direction or you come in with the anti-clockwise direction. Similarly, if you look at this part VBC, so opposite of this one is the VCB, that is exactly at the angle of 180 degree from here, right? Similarly, if you look at VCA, so opposite of that is VAC at the angle of 180 degree from VCA. Okay, now let's look at the equations which are going to define these voltage waveforms. Let's suppose that VAB is defined by this equation where VLM is the peak voltage of the line voltage waveform. So peak value of line voltage, right? Now if you represent VAB with this equation, then VBC will be represented by the delay of 2 pi by 3. So that you can see over here, the VBC is equal to VLM into sine of omega t minus 2 pi by 3. Here is the delay of 2 pi by 3. And how to get the VCA will be further delayed by 2 pi by 3, so its total angle will be 4 pi by 3. So these are the line voltages waveforms, VAB, right, and then VBC at the angle of 120 degree from here, and then VCA, that is over here further at the angle of 120 degree. So these are the phasors for the line voltage waveforms. And how to get VBA? VBA will be obtained by taking the difference of pi. So we are going to add pi in this one, so we are going to get this one as a equation for VBA. Similarly for VCB, if you add pi in this one, so you are going to get this one, and simplifying you will be getting this one, VLM into sine of omega t plus pi by 3. Then VAC will be obtained by adding pi in this one, so if you add pi in this, so you are going to get this one. So from the reference, the reference line is this one. You can look at all of these angles at any instant of time. Okay, now let's look at the operation of this half control rectifier for the firing angle which is less than 60 degrees. So we have discussed its waveform in the last lecture, so I will be briefly introducing it again. So here you can see we are going to define some reference point. This is the reference 1, this one is the reference 2, and this one is the reference 3. We have 3 thyristors and 3 reference points. So we will be calculating the angle of the particular thyristor from this reference point, angle alpha from here, angle alpha from here, and the angle alpha from here, where alpha is the firing angle. If I say that we are going to fire this thyristor at the firing angle alpha, it means we are going to apply the pulses at these positions, right? And for symmetric firing angle, all of these firing angles will be same. If alpha is equal to 30 degrees, so this will be 30 degree from its reference, this will be 30 degree from its reference, and this will be a 30 degree from its reference. So we will be applying these gate pulses to our thyristors, and when we are going to apply the gate pulse to the first thyristor T1 at this position, so at this point VAB is maximum, so the conduction will be there from phase A to phase B, and in the reverse direction the diode of phase B, that is D1, that will be turned on. So during this interval of time that you can see over here, that T1 and D1 are in the on state. So during this interval T1 and D1 will be on. Right from this point onward, the voltage VAC is maximum, so you have turned the thyristor of phase A on by applying the pulse, so reverse path will be towards the phase C. So this diode D2 will be turned on, and the voltage, this voltage will be appearing across your load. And then you will be applying the gate pulse to your second thyristor T2, so at that point VBC is maximum, so the conduction will be there from B to C, and this portion is going to appear. Then over here there will be a commutation in the diode from diode 2 to diode 3, and then you are going to apply the pulse to the next thyristor. So then the thyristor commutation will be there from T2 to T3, and then the diode commutation right at this point, because this is going to become maximum over here. So here you can see one cycle of the output voltage waveform, that is this one, right, and this will be repeated periodically because you will be applying the pulses at every 120 degree. Here you can see first pulse was applied over here from this at the angle of 120 degree, second pulse is applied, and then at the angle of 120 degree third pulse is applied, and so on. So this is the voltage waveform for the firing angle of alpha, but this alpha is less than 60 degree. Okay, now how to get the output voltage waveform? For that we are going to consider this portion, and you can see this is being repeated 3 times, 1, 2 and 3 across the output voltage across the load in one supply cycle. So we will be just considering one part, and then we will be multiplying it with 3 to get the total area under the curve, and for the average we will divide it by 2 pi. So VDC will be equal to 3 times the area of this one, so that's why you can see 3 over here. For average you are going to divide it by 2 pi, right? And okay, now let's look at this one, VAB. So what for this portion will be available across the load from the angle alpha, right there. If we consider this one as the reference point, so this angle is pi by 3, because at every 60 degree there will be the crossing of the line voltage waveforms. So this point will be at angle of 60 degree, that is pi by 3. So from this point if you look at this angle alpha, so what will be the angle of this point? Alpha plus pi by 3. So this is this angle starting point, and this is going to appear across the load up to this point, and this is 2 pi by 3, and then 2 pi by 3. So we are going to integrate from pi by 3 plus alpha to pi by 3 voltage waveform VAB, right, because this is going to appear across the load. And then we are going to integrate VAC from 2 pi by 3 to this point. And what is this one? This will be equal to alpha pi plus alpha, right, because this is point pi in terms of angle and the alpha from here. So this will be pi plus alpha. So we are going to integrate from 2 pi by 3 to pi plus alpha the voltage waveform VAC, right. This is the position pi, and then you are going to find at angle alpha from here onward, because this is the reference point of the second thyristor. So the limit will be from 2 pi by 3 to pi plus alpha, and the voltage waveform will be VAC, right. So now if you take the expression of VAB and VAC that we have previously seen, VAB is equal to VLM into sine of omega t, and VAC will be equal to sine of omega t minus pi by 3. So now if you go through these simple mathematical steps, trigonometric identities, so finally you will get the VDC for your half control rectifier given by this expression, right. And for the RMS value, you will have to take the square of this one, and then you will have to take the under root. So if you do it, so this will be written like this, right. So VAB square, then the square of VAC, integration for the mean value, and then multiplying it with 3, because 3 times this area is going to appear, and then the under root. So the RMS value will be given by this expression for this particular output when your firing angle is between 0 and 60 degree. So from 0 to 60 degree, this expression will be used for calculating the DC voltage and the RMS voltage. Now let's quickly look at what will be the situation at the angle of 60 degree. So this is the reference point, this is the reference point, this is the reference point. So we will be applying the pulse to the first thyristor at angle of 60 degree from its reference point, 60 degree for the second thyristor, but its reference point is this one, and the reference point for the third thyristor is this one. So we will be applying the pulse at this position. Okay, so when we are going to apply the pulse at the thyristor T1, so along with that the diode D2 will be turned on, because VAC is maximum in the circuit at this instant of time. VAC is going to appear. So from phase A towards phase C, so D2 should be turned on. So T1 and D2 will be on from this point till this point until you are going to fire the next thyristor. So you are firing the next thyristor right at this point by applying the gate pulse. So from this point onward, VBA is the maximum, and that will appear across your load until you fire the next thyristor, right. Why you will be waiting for the next thyristor? Because you can see it is VBA and VCA. So VBA, thyristor of phase B, is turned on by applying the gate pulse over here. So in the positive side, over on the high side, your thyristor 2 is in the on state. In the reverse, there will be the in diode connected with the phase A will be conducting, that is this diode 3. So diode 3 is conducting and your thyristor T2 is on. You are not going to apply the pulse to other thyristors, so this voltage waveform will keep on appearing across the load. So from this point till this point here, these two switches will be in the on state, and then over here you are going to apply the gate pulse to the third thyristor. So T3 and D1 will be conducting. So these are the conducting devices, and you can write down the integral equation to determine the DC voltage at the average DC voltage at the output. So VDC will be equal to 1 by 2 pi. There are 3 portions, so multiplying by 3, and then integrating one waveform, and that is V AC, right, and VAC and its limits from this point. So what that will be equal to? So over here it is the interval of pi by 3, right, and sorry, pi by 6, and then from this pi by 6 your firing angle will be the angle starting point, right. So the firing angle is of 60 degree over here, right. So 60 degree from here you can see the pulse at this position, right. So basically you are going to start from 2 pi by 3. So from 2 pi by 3 and till this point, what is this one? This is equal to 4 pi by 3. So 4 pi by 3, integrating this VAC, right, with respect to d omega t. So this will give you the average DC voltage at the output, right? So you will be taking the equation of VAC over here, and that we have seen in the previous slides. Okay, now looking for the firing angle of 90 degree. So for firing angle of 90 degree, this is the, first of all, let's mark down the reference point. This one is the reference point for the first thyristor, for second thyristor, and then for the third thyristor. So from this, the angle of 90 degree will be this one. So you will be applying first gate pulse at this position, and then from this reference point, the angle of 90 degree will be this point. Second thyristor will be fired over here, and then from this reference point, 90 degrees this point. So you are going to fire the third thyristor at this point. So you are applying these three gate pulses, and this voltage waveform will appear, and there will be no negative part over here as we discussed in the last video, because we have the resistive load. However, for the highly inductive load with the freewheeling diode, you will be getting the same waveforms for the firing of 90 degree, right? So the equations for the VAB, VLM is VLM into sine of omega t. This is VAB. Then VBC will be at the angle of 120 degree, and VCA will be at the angle of minus 240 degree, and VAC, that is the 180 degree out of phase of that one. So for that we are going to add pi. So that is this one, VAC. So you can integrate this VAC. You have now the expression for this one from over the certain limits, and you can find out the average DC voltage at the output by multiplying the area of this one by 3. So now let's calculate that one. So if you look at the limits, so for the limits we can look for that one, pi by 3 plus alpha. So this is the pi by 3 point, 60 degree point, and from here your pulse will be applied at angle alpha. So pi by 3 plus alpha, right, this one in generic, but alpha is 90 degree at this point, but we are writing expression in generic. So pi by 3 plus alpha, and this will be conducting up to this point, and this point, if you look at from here, is equal to 4 pi by 3, right? So integrating from pi by 3 plus alpha to 4 pi by 3, dividing it by 2 pi for the average, and 3 such portions are going to appear, so there is the multiplication with 3. So now you are going to integrate VAC over here, right? So taking the expression of VAC, so it will be VLM sine of omega t minus pi by 3, and then going through the simple mathematical steps, integration steps, so you can write down the output DC voltage like this, right? And what is this V? And this is basically the peak voltage of the phase. In terms of line voltage, the expression for the DC voltage is this one, when your firing angle is 90 degree or above 60 degree, right? Because why we are going to consider it above 60 degree? Because up to 60 degree, you can see this is the waveform. Above 60 degree, if there will be highly inductive load, the negative portion is going to appear, and if there is the resistive load, then there will be a zero level over here in the case when you have the firing angle above 60 degree. So that's why for the firing angle up to 60 degree we use this expression, and for the firing angle above 60 degree we use the second expression that we have seen over here. So this one, so this is used for the firing angle above 60 degree. Okay, now for the RMS value, you can take the square of this expression and then the under root, and if you simplify, you are going to get this expression for the RMS value at of the output voltage waveform. Now let's quickly look at the fully controlled bridge rectifier. In the case of fully controlled bridge rectifier, there are the 6 thyristors which are turned on and off at certain interval, at certain instant of time, and you get the required output voltage waveform. So whenever you are going to turn on the particular pair of the thyristor, let's suppose T1 and T6, so it will be applying the voltage VAB across the load. And if you turn on some other pairs, let's suppose T3 and T2, so you will be getting VBC across the load. So depending upon the switching pair, you will get the output voltage at the load terminals. Okay, so now let's look at that if we are going to fire our thyristor at the 0 degree, that you can see over here T1 and T6, two pulses are applied. So from this point onward, VAB is going to appear because the conduction is there from phase A to phase B because of these two thyristors T1 and T6. T1 is this one starting from phase A and then from T6 back to phase B. So A to B conduction is there, and VAB, this voltage is going to appear across your load. Then at this point we are going to turn on thyristor T2. T1 was previously turned on, so when you are going to turn on T2, that will turn off T6, and the current in the reverse will start flowing through the thyristor T2. So this will be the part starting from T1. Now through the thyristor T2, the current is returning back. This thyristor is turned off because of the turn off of the thyristor T2. And then over here we are going to apply the gate pulse to T3. So T1 will be turned off, and T2 and T3 will be conducting, right? And so on. So you will keep on applying the pulses at these reference points. From these reference points, these are at the angle of 0 degree. There are 6 reference points now because we need to generate 6 pulses, and the angle between these two, any two pulses, is 60 degrees. So once you locate the first pulse where to apply for the firing angle of 0, then with respect to that, every 60 degrees you will be applying the next pulse to the next thyristor, right? And now how to find out the average output DC voltage? Let's consider only this part. And if you look at this one, VAB is there, and the limits of integration will be from pi by 3 to 2 pi by 3 in the case of alpha equal to 0. But if you are increasing the firing angle, as you can see over here for the 60 degree, this one is the reference point, these are the reference points. So you are going to apply the pulse to the first thyristor at this position, second thyristor over here. So all the pulses are delayed by angle alpha, right? So now if you consider this one as the reference point, this one as the reference point, this one, that is the angle of pi by 3. So pi by 3 plus alpha, so pi by 3 plus alpha will be the starting point, and this next pulse is applied at the angle of 60 degree, right? You applied the pulse over here, and the next pulse you are going to apply over here, so angle of 60 degrees. So whatever is the angle of this one, that is pi by 3 plus alpha, adding pi by 3 in that one, you will get the upper limit. So you are going to integrate VAB from this pi by 3 plus alpha to 2 pi by 3, right? And this will be repeated 6 times. 6 equivalent to 1 2 3 4 5 and 6. So 6 times it will be repeated, so multiplying it by 6. So you will get the total area, and to get the average area you are going to divide by 2 pi. So if you take the expression for VAB over here, VAB will be sinusoidal waveform sin of omega t, so that you can see over here. Now if you simplify, so applying trigonometric identities, you will get the DC voltage given by this expression, where VLM is the peak value of the line voltage. However, if you write in terms of the peak value of the phase voltage, so this VLM is equal to under root 3 times the peak value of the phase voltage. So you will be getting this expression. Okay, here you can see the RMS value as well. How to get the RMS value? RMS square will be equal to this expression, but you will have to take the square of that one, right? So VLM square sin square omega t, 6 by 2 pi will be written as 3 by pi, and that will be equal to VRMS square. So if you simplify this one, you will get VRMS, that will be given by this expression. Okay, so we have obtained the expression for the DC voltage and the RMS voltage. Now we quickly go through the output voltage waveform at the angle of alpha, that alpha is 60 degree in this case. I'm talking about this figure, alpha is equal to 60 degree. So if you are going to apply the pulses at the 60 degree from the reference points, right? So reference points is this one, this is first reference. From here you can see the angle of 60 degree, and then for the second pulse, that is delayed by 60 degrees. So your output voltage waveform from the 3-phase fully controlled rectifier will be this shaded one. Okay, so now quickly moving toward the firing angle of 90 degree. So these are the reference points of the thyristors. So from here at the angle of 90 degree you will be applying the first pulse. So that is this one. You are going to turn on thyristor T1. The reference point for the second thyristor is this line. So from here you can see 90 degree. This is the pulse for the second thyristor, and similarly from this point at the angle of 90 degree, third thyristor, fourth, fifth, and so on. So you can refer to the last video for the detailed discussion of this one. So we are going to generate these 6 gate pulses, and whenever you are going to previously T6 was on and you are going to turn on T1 along with that one, so that voltage will appear, that will be there in the loop, that will be completing the loop. So from thyristor, let's suppose we have this path, so VAC will be appearing, and if we have this path, so VAB will be appearing. So depending upon which pair of the thyristor is turned on, you can find out the voltage that will be appearing across your load. So for firing angle of 90 degree, this is the voltage waveform that will be appearing across the load. So if you want to find out the DC value, so you will have to look at one part and then you will have to decide about the limits. So let's take the very first pulse that will be appearing. T1 is there. Let's look at this one. So the reference point is at pi by 3. So what will be the angle of this point? Pi by 3 plus alpha. So that will be the starting point, and once this will start appearing across the load, it will appear up to this point, that is the zero voltage level of your voltage waveform. And so this is we are going to consider the portion of VAB over here, right? This is the portion of VAB. So for VAB, this is the point pi, so we are going to integrate it up to pi. So pi by 3 plus alpha 2 pi integrating VAB, so you will get this area under the curve, and then you will multiply it with 6 to get the total area in one supply cycle, and for the average you are going to divide by 2 pi. So if you simplify, you will get this expression for VDC, and for RMS you will have to take the square of this one, and taking the square, then simple mathematical steps are there, so you will end up with this expression, right? Okay, now finally, if there is the highly inductive load, then you will see the negative voltage for the firing angle of 90 degree at the output, and the average DC voltage will be 0. If you consider, if you go and look at this resistive load, there was no negative part in this one, because the thyristors are going to turn off over here automatically, because the current is going to become 0. In the resistive load, your current waveform will be of exactly same shape as that of the voltage waveform, but in the case of inductive load, your current will lag behind, and current will not be reaching to 0 right at this point, it will be extended. So that's why your diodes will be your thyristors will be in the conduction state. So for highly inductive load, we will be getting this waveform for the firing angle of 90 degree. However, if you connect a freewheeling diode across the load, then you will be getting this waveform, because the negative part will be chopped. So let's conclude this video. In this we have discussed about the voltage waveform and the calculation of the DC voltage and the RMS voltage for different firing angles for half control and fully controlled rectifier circuits. That's all from this video. Thank you very much.